Hey everyone, Austin Meyer here, and today I'm going to talk a little bit about wing sweep in X-Plane 12. But before I talk about wing sweep, I'm going to talk about something that drives wing sweep. The reason we even have wing sweep in real airplanes. And that thing is called the critical Mach number. The critical Mach number of an airfoil. That is the magic number that makes wing sweep a necessary thing. Here's how it works. Let's imagine for a moment that you've got an airfoil and it's moving through the air at 80% of the speed of sound. Well, if the airfoil is coming forward at 80% of the speed of sound, you've got to admit that the air is going to go faster than 80% of the speed of sound to get out of the way of the airfoil. Think about it. The air's got to accelerate up over the top of the foil or accelerate down underneath the foil. I don't care if you call this Bernoulli or anything else. Air has got to get out of the way of the airfoil when it arrives. The airfoil is made out of metal after all. Air doesn't go through it. And so let's just say hypothetically that the air speeds up by 25% to get out of the way of the foil. Well, if the airfoil is going Mach 0.8 through the air, you add another 25% for the air to get out of the way of the foil, the air just hit Mach 1. You just got supersonic flow around an airfoil that's only going 80% of the speed of sound. That's what happens when the air has to get out of the way of the foil. Now, the exact Mach number that this happens is different. Thin foils can get through the air very close to Mach 1. Thick foils, well, they have to go quite a bit slower before the air hits Mach 1 because the air gets out of the way more. And in fact, a round like cylinder going through the air can literally only go through the air at 37.5% of the speed of sound before you start getting shock waves around the foil. Apparently, according to all the math I've researched. So this number, the speed at which a foil can go before you start to get supersonic flow around it, is called the critical Mach number, or M-crit is how they refer to it in shorthand, the critical Mach number. Let's take a look at how that would form. So let's say you're flying at Mach 0.72, the critical Mach number. The maximum local velocity is less than sonic. In other words, the air getting out of the way of the wing is not hitting the speed of sound yet. Then you speed up to say Mach 0.77. The airfoil starts seeing supersonic flow. Look, the air is accelerating over the top of the foil, and as the air accelerates over the top of the foil, yeah, there's a region that's supersonic. And as soon as that happens, the drag goes through the roof. Oh my gosh, because it's not just, oh, supersonic flow bad. Oh no, you're getting supersonic flow. It's hitting a shock when it slows down behind the point of highest velocity over the wing. And then that shock makes all kinds of wake and waste energy and goes kaboom, you know, all that stuff. You're wasting energy at that point. So in other words, if you want to operate efficiently, you need to operate below the critical Mach number. If the critical Mach number of a foil is 0.75, you better fly 0.74. Because if you get up to 0.75 or 0.76, the airflow is going to accelerate to Mach 1 as it gets out of the way of the foil at its thickest point, and it's going to generate a shock wave, and it's going to make nothing but noise. Heck, you go even faster, you can even get some shock waves on the bottom as well. It's wherever the air has to get out of the way of the foil. So let's look at a NACA 4412. This is your standard kind of old school high lift foil. And I just kind of penciled in red there where the flow would hit supersonic first. While this foil might be doing 0.75 or something like that, the air is accelerating over the top to produce, you know, low pressure and high lift and all the things we like out of wings. But that low pressure isn't associated with the air speeding up, of course. When the air speeds up to Mach 1, boom, there's your supersonic flow. There's your shock wave on the back. You see how it's kind of fuzzy up front as the air accelerates, and then kind of sharp in the back when it hits that shock? And so this is your region of supersonic flow. And so people back in World War II, they were like, well, we want to go faster. We're in a hurry. We got to go faster. But we always get into these shock waves from air going supersonic as it gets out of the way of the airfoil, even though the airfoil is below the speed of sound. Is there something we can do? And they researched something called supercritical airfoils. Now, in addition to having the coolest damn name in the world, supercritical airfoil, oh my God, what an awesome name. What this does is you'll notice it doesn't really have a fat section up top, does it? This is a supercritical foil, and once that air has just gotten out of the way of the foil, it doesn't continue to accelerate anymore because it doesn't get a lot fatter up here. You see, the air doesn't have to speed up anymore. And so while with the regular old airfoil, you'll get this shockwave building up, here you really don't get that because the air just doesn't have to get out of the way. Not as much because it's not so fat and raised up in the middle. Now, you start saying, well, I want some dang lift. How do I get that? Well, maybe you kind of pop a little downwash down in the back or something like that to get your lift. Maybe pop the air down with the downward trailing edge. Maybe get yourself a little equal and opposite reaction, or maybe the low pressure is just kind of back here, you know, as the air gets kicked down. And you'll notice the airfoil is thickest way back here, way back, close to the back of the foil. And that's so the air has plenty of time to get out of the way. You see here, the air only has the first 25% of the foil to get out of the way of the thickest part of the foil. Boom, that air speeds up and you hit sonic. Here with the supercritical foil, the thickest part is way back here. And so the air might accelerate to 0.95, 0.95, 0.95, and only just finally hit Mach 1 way back here at the back. And so while this airfoil cannot go supersonic without encountering shock waves, it can get closer to supersonic before a shock wave happens by delaying how much the air speeds up. And it delays how much the air speeds up by flattening that top so you don't get that high speed, low pressure above the foil, and delaying the thickness, the point of maximum thickness of the foil until way at the back. And that gives you longer, more time to get out of the way of the foil, which means it doesn't speed up as quick, which means it stays below Mach 1 for longer, even as the aircraft keeps accelerating. And so a supercritical foil can give you about another 0.1 Mach. And so here's a rule of thumb. An old school foil that's not really designed to go fast, its critical Mach number is going to be 0.85 minus the thickness ratio. So if this thing is, well, it's a 4412, it's 12% thick, your critical Mach number is going to be about 0.85 minus 0.12, right? 0.85 Mach minus 0.12, the thickness of the foil, that's 0.73, right? And so your critical Mach number of this foil is probably right around 0.73. But a supercritical foil, which is designed to be as fast as possible, they get a Mach number of 0.95 minus their thickness ratio. And so if this thing is, well, maybe it's 14% thick, if 714 means 14% thick, I don't know if it is, it looks like it might be something like that. So if this is 14% thick, then your critical Mach number is going to be 0.95 minus 0.14, which is what, 0.81. And so this foil managed to get a little faster. I'm not sure if I got the thickness on these foils right, but either way, the critical Mach number of an old school non-supercritical foil is going to be 0.85 minus the thickness of the airfoil. The critical Mach number of a supercritical foil is going to be 0.95 minus the airfoil thickness. All right, so now you understand approximately what the critical Mach number is. It's as fast as you can go before you run into transonic drag and shock waves. So you need to operate your airplane below that critical Mach number. You understand that the thicker the foil, the lower the critical Mach number. And you understand that supercritical foils let you get another 0.1 Mach faster before shock waves form by delaying shock wave formation. And so something like this is going to have a critical Mach number of 0.85 minus the thickness. Something like this is going to have a critical Mach number of 0.95 minus the thickness. And by the way, in Airfoil Maker, you enter the critical Mach number. You just go to Airfoil Maker, and the Airfoil Drag Divergence Mach is what I used to call it, starting with X-Plane, RC4, RC5 or so, when these user interface changes are rolled in. You'll see I don't call it the Drag Divergence Mach number, I call it the critical Mach number. And in the new versions you'll get soon, you'll actually see a little recommendation here on what I think the critical Mach number should be based on the airfoil thickness you've entered. So that's critical Mach number. And the thing you may have noticed is you're limited to like 0.75 or 0.85 Mach, something like that. Well, people want to go faster than that. Oh, and it gets worse. As you start going to a positive angle of attack on these wings, you start getting more suction on top. More suction came from more speed. More speed means you hit shock waves, over the foil, even at a lower speed. And so these critical Mach numbers I gave are when the airfoils aren't producing any lift. Once you start pulling up and producing lift, their critical Mach numbers come down, way down. Actually take the lift coefficient, multiply it by 0.1, and that's how much the critical Mach number comes down. So in other words, if you've got a critical Mach number of 0.75, but you're pulling a lift coefficient of 1, you need to subtract 1 times a tenth, which is 0.1. Your critical Mach number is going to go from 0.75 down to 0.65. Well, that's not jet speed. If you can't even go 0.65 before you start getting shock waves, because your airfoil is also putting out lift, which is speeding up the air and creating lift, suction and lift over the top of the wing. If you can't even go 0.65 before you start building up shock waves, you're in for a pretty slow airplane. So how do we get around that? That's a question people were grappling with. And at the end of World War II, the United States was starting to build the next generation of bombers, things like the B-52, B-47. And the United States was putting these airplanes on the drawing board, jet airplanes with straight wings. And somebody going through all the German archives found that the Germans were researching swept wings and said, whoa, 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 hold the presses, hold your production, don't build a straight wing airplane. The Germans found out near the end of World War II that if you sweep the wing of an airplane, you can go through the air a lot faster. And then as soon as the people at Boeing and whatnot saw these reports pilfered from Germany, they're like, we got to sweep the wings of the B-52. And so wing sweep was discovered right during the end of World War II by the Germans and then eventually ported over to the United States. So let's take a look at how wing sweep works. So a regular old wing here of a Cessna, this is just like one of these cross sections, right? As the air is hitting the wing, it speeds up going over the top, just like you see here or here or here, and then shock waves form. And so even if you were to like dive in a Cessna, well, you couldn't do this in a Skyhawk for other reasons. But in a straight wing airplane, if you were to dive, by the time you get to maybe 0.65 or 0.7 Mach or so, your shock waves start to form over the wing. You can't go any faster. The X1, by the way, to head off YouTube comments, well, the X1 was a straight wing and it broke the sound barrier. Yeah, but that wing was paper thin. The leading edge of that wing would like cut you. It was so sharp and thin. So given that you want to have a thick enough wing to hold some fuel and make some lift in most commercial airplanes, this critical Mach number of 0.65 or so after you've taken out the lift coefficient is a blockade to speed. So how do you solve it? You sweep the wing, okay? And when you sweep the wing, the component of air that is actually attacking the wing is just a component that's like at a right angle to the spar or a right angle to the leading edge or technically a right angle to the 25% chord. You see, a swept wing gets out of this direct confrontation with the air and kind of slides through the air sideways, kind of gets out of that direct confrontation. And so imagine if this wing was swept way, 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 way back, then there would be almost no airflow at all migrating from the leading edge to the trailing edge, right? Imagine this wing swept back 85 degrees. Well, there would be no air at that point migrating from the leading edge to the trailing edge. The wing would have basically no lift. And it would also have no drag, and you would also be able to get very, very close to Mach 1 without forming any shock waves. And so when you sweep the wing, the effective airspeed is equal to the true airspeed of the airplane times the cosine of the wing sweep. In other words, the effective airspeed over the wing is just the component of air that's migrating from the leading edge to the trailing edge. And I've known this since X-Plane 1, and this has been coded since X-Plane 1. However, in version 12 betas and in version 12 RC1 and RC2, so in the version 12 betas and RC1 and RC2, I erroneously applied the full speed of the air to swept wings, not just the component that is migrating from leading edge to trailing edge. In other words, I took out the cosine sweep term. And so that was me. And then Mike Vivaldi, impersonated here, or demonstrated here by this guy, came along and said, Austin, you messed up wing sweep. You got to tell me what the heck you're doing because I say you're wrong. And at first I was like, I'm not wrong. And I did the math and I was like, oh yeah, I am wrong. So that's Mike and that's me. So starting with RC3, X-Plane 12, RC3, thanks to Mike calling it out, I've corrected the wing sweep by returning the cosine sweep that I've had back since X-Plane version 1. And So what happens is, let's say your sweep is 45 degrees. The cosine of 45 degrees is 0.707. So even if you're doing 100 knots of airspeed, you take 100 times 0.707, which is 71 knots, which is a component of speed making it from the leading edge to the trailing edge. And here's why this is so darn useful. It means that even though your critical Mach number might start off at 0.85 minus the wing thickness, let's say 10% wing, that takes your critical Mach number down to 0.75, minus the reduction you get from producing lift, let's say your coefficient of lift is 1, then that takes your critical Mach number down to 0.65. You've now got a critical Mach number of 0.65, but you want your airplane to go faster than Mach 0.65, so you sweep the wing. So the effective speed over the wing is now only 71% of the actual speed of the airplane, and that gets you that much faster, because even though the airplane, like the Citation, might be doing Mach 0.9, the speed over the wing is only Mach 0.9 times the cosine of the wing sweep. And so the speed over the wing might be Mach 0.65 or Mach 0.7, which you can just barely get below your critical Mach number. And what's so cool is when I put this code in after Mike called it out and I started checking it with all my airplanes, all my swept wing airplanes, the Citation, the A330, the Boeing 737, the MD-80. These are all swept wing airplanes. They're all hitting their performance according to the books in X-Plane 12 now, starting with RC3. They're all hitting their performance according to within 1% of their Mach number in N1. And every single one of them is just starting to get transonic drag rise over the wing roots. The root where the incidence is the greatest and the wing thickness is the greatest for structure and holding landing gear and fuel and all that. We're just starting to tickle this thing here. The wings are just barely going over their critical Mach number and just starting to get the tiniest little bit of supersonic flow over the top of the wing. They're just touching it. And so the cruise speed of these airliners is literally determined by the critical Mach number and then the speed is multiplied by the cosine of the wing sweep. And so the speed these airplanes actually go, it's the same. I don't care if you're a McDonnell Douglas MD-80, a Boeing 737, an Airbus A330, or a Citation 10. All of these airplanes effectively for the wing go the same speed. It's about Mach 0.65 or so over the wing. And it's just various degrees of sweep that let them go a little bit faster before they hit that critical Mach number of about 0.65 or so over the wing root. Over the tip, it's not so critical because the wing's a lot thinner out there and puts out less lift. But over the root, where that wing is thick and puts out a lot of lift with all that incidence, that's where the shock waves form. Every one of these airplanes has got shock waves just starting to form, barely starting to form over the wing root. They're all touching critical Mach number. And the MD-80 is the slowest of the bunch because it has the least wing sweep. The 737 and the MD-80 is the slowest. The 737 and the Airbus A330, they got more wing sweep. They go a little faster. The Citation 10, he's got the most wing sweep of all. He goes the fastest of all. So the secret is all these airplanes have the same critical Mach number over the wing. The Citation and the swept wing airplanes just go faster because they get out of a direct confrontation with the air. They slide through it sideways. The effective speed over the wing is equal to the true airspeed of the airplane times the cosine of the wing sweep. So I coded all this. I checked all my work. And let me just show you quickly how you can enter this into Plane Maker and Airfoil Maker yourself if you're an author making aircraft with swept wings. Number one, for your airfoil thickness in Airfoil Maker, make sure you enter the correct airfoil thickness to your foil. And then above all, enter what I used to call your airfoil drag divergent Mach number, which I now call your critical Mach number, and take either a 0.85 for an old school foil or a 0.95 for a critical foil, subtract the thickness ratio, and that is the airfoil drag divergent Mach number or critical Mach number for the airfoil you should enter. And future versions of X-Plane, I've already coded this, it just hadn't been tested, moved into release yet, but future versions of X-Plane will suggest the critical Mach number to you right here to help you out there. But use the numbers I just gave you in this video to enter your airfoil drag divergent Mach number. That's going to cause shock waves to form over the wing and the drag to shoot up at just the right speed. The next thing you want to do is get your wing sweep correct. Whatever the wing sweep is of the real airplane, enter it properly in Plane Maker. It's critically important because that's what's going to say that even if the airplane's doing 600 knots, and the wing sweep's 45 degrees, then the speed on the wing is going to be 600 knot times cosine of 45, which is quite a bit lower speed, which hopefully will be below your drag divergent Mach number even after the lift coefficient further lowers your drag divergent Mach number. So enter your wing sweep correctly. Then, once you've done that, and this is pretty fundamental stuff here, once you've done that, you want to get your low speed performance correctly. Or correct. You want the airplane to stall at the right speeds and have the right attitudes on approach. So when you lower your flaps all the way, adjust your flap coefficient of lift as necessary to get the airplane to stall at the right speed or have the right pitch attitude at approach speed and weight. And flaps spit out a wide variety of coefficients of lift depending on how many slots they have and how big they are and how much they deflect on the shape of the foil and the shape of the flaps. But enter the number here in flap coefficient of lift that causes the airplane to stall with the flaps down at the correct speed. If you don't know the stall speed, well then to fly your approach at VREF at the right speed with the appropriate pitch attitude once you've checked your weight. So that's entering the airplane properly. This is tuning the approach speed. Now let's talk about tuning the cruise speed, which I know you also want to hit. In my experience, and hopefully there'll be some good YouTube comments that can do better than my experience, but in my experience, inlet compression efficiency in the engine screen and plane maker should run about 95%, and a normal shock for the engine might be 0.95. In other words, you have to go pretty fast before you start really close to the speed of sound, before you start getting a normal shock across your engine inlet. And inlet compression efficiency seems to be very, very, very efficient. Because remember, the inlet on a modern jet airplane expands. It's a diverging duct. And so even though the inlet, the air hits that inlet at say Mach 0.8, if that's how fast you're going, the inlet expands, which slows the air down to maybe Mach 0.6 or something like that before it hits the compressor face. So the first bit of slowing the air and compression is done by the inlet of an airliner. And it seems to me that that process is something in the ballpark of 95% efficient. I could be wrong about this, but when I put this in, I get the airliner performance that I would expect. And so if anyone from Boeing or Airbus or Bombardier or something that knows better than me, feel free to comment below or email me at austin@xplane.com and tell me what the inlet compression efficiency really is as air expands in the inlet of an airliner. And I'll be happy to do a new video or replace this video with an updated one that gives the correct number. But once you've entered, I recommend 0.95 for each of these. The next thing you want to do if you want to get the thing to cruise to the right speed is in the fuselage or the bodies. So you go to the bodies and you enter the body coefficient of drag. So I look at the fineness ratio of the body and I give you an estimate on what the drag coefficient might be in plane maker. So you could enter that, but I found from experience you need to bump it up by 50% or so. Because my estimate is based on a perfectly streamlined body with no wings, no antennas, no wing fairings, no landing gear fairings bulging out, no cockpit windows, no rivets, no seams, no windows, no interference drag, no excrescence drag. Basically, my drag estimate is the perfect world. It's like a perfect glass, shape that has just no imperfections in it at all. I found from experience in real airplanes, by the time you get the interference drag of adding in the wings and the cockpit windows and all those stuff, you need to have like a 50% higher value than my recommendation when you start to get into the real world. The other thing you might want to enter is an area rule ratio. Here's what that is. So the area rule ratio, enter 1 if you want the body to have like no concept of area ruling. So here's what area ruling is. Area ruling is where the airplane, and this is a little bit surprising, the airplane is a constant diameter from the nose to the tail as much as possible, a constant diameter nose to tail. In other words, if it starts really thin and then gets really wide and stays wide, or gets really wide and then it gets really narrow at the end, that's actually surprisingly bad to go close to the speed of sound. Why? Because shock waves start forming over the fat part of the body. Right? The fat part of the body, that's where the air gets out of the way the most, that's where the shock waves form, that's where the drag happens. But if you want to get close to the speed of sound, you don't want to have one part that's fatter than the other, where the air suddenly has to get out of the way and form shock waves. You want more of a constant thickness along the length of the body. Something that looks like this, like the supercritical airfoil. Well, what do you know? Our friend the supercritical airfoil is back to talk to us again. Now to tell us that an airplane fuselage should also be kind of like this, more or less a constant width along its entire length of the body if you want to get close to Mach 1 without having shock waves forming over a thick part of it. And so an area-ruled aircraft will have a more or less constant thickness along its entire length. And if you look at the Citation 10, it's got a gigantic wing fairing that starts way up at the nose, all the way up at the nose, then kind of like seems to disappear a little bit under the wing, and then is really apparent back behind the wing and back to the tail. Why is that? Well, that fairing is trying to area rule the airplane by building up some thickness up here and then kind of disappearing where the wing is. So as the air goes around the wing, it has a place to get out of the way and go up under where the fairing would be. It's trying to keep a constant cross-sectional area from the nose to the tail, getting skinny where the wing is. You'll also perhaps notice that the fuselage gets a little skinny here in this airplane. Why does the fuselage get a little skinny here? Well, it's trying to get out of the way of the engine. The engine's walls are going to add some volume, and so you let the fuselage be skinny to let the air get around the engine without getting bunched up in there and hitting shock waves. So area ruling, look at the, there's an airplane called the Thud. The Thud. If you Google image of the Thud, I'll probably drop it in the video, you'll see the airplane gets kind of skinny in the middle. Why does it get skinny in the middle? Well, because that's where the wings are. And so it keeps a constant cross-section. As the wings add cross-section, the body gets skinny to take it away. And so if you enter an area rule of 0, then that means your airplane has no area ruling at all. There's no thought given to transonic flow. It's like a Cessna 172 or something. And as you start to get close to Mach 1, drag is going to build up on the body as this starts to happen on the body, just like with the wings. And if you enter an area rule ratio of 0, the ratio is a supersonic drag fraction. If you enter an area ratio of 0, well, that assumes the airplane is perfectly area ruled so that no shock waves form on the airplane until it hits Mach 1. And I don't think any airplane's ever been designed that can actually do that. And so I think I entered 0.5 for the Citation as my first guess, and sure enough, the performance was hit. That's the Citation 10, which is a carefully area-ruled airplane. So my first guess is that we could get halfway to perfect area ruling with all their careful fairings and body sculpting and all that they do. So I guess the summary is enter your airfoil thickness properly, enter your your critical Mach number according to the formula I gave early in the video, enter your wing sweep properly, enter the flat coefficient of lift as necessary to get your low speed performance and stall speed, enter a 0.95 for inlet compression and normal shock, enter a drag coefficient maybe 50% higher than I recommend, and tune that as necessary to hit your cruise numbers, and enter an area rule that is 0 in a perfect world that never exists, 1 for an airplane that is not area ruled at all, it's 100% of the drag, or maybe 0.5 for the Citation 10. I found it worked really well. And so when I did all this, all the airliners started flying just perfectly, and you'll get all the benefits of this in X-Plane 12, RC3, and later. But one weird little thing went wrong. When I did all this, the F-14 started flying terribly. The F-14 seemed to suddenly lose authority over the horizontal stabilizer. And it's like, oh no, I thought I finally got the math right. Why is my F-14 suddenly not having enough stabilizer authority? What went wrong? And then it suddenly occurred to me, the F-14 doesn't have a regular wing for a horizontal stabilizer. The F-14 has what's called a delta wing. All right, let me see if I can stand here. All right, hopefully y'all can see everything you need to see here, including me, and you can get enough light. The F-14 has a delta wing for a horizontal stabilizer. Now, what is a delta wing? A delta wing looks like this, where it's like a triangle type thing where air rolls up around the leading edge. And when the air rolls up around into the leading edge, it forms these vortices, primary and secondary vortices. What are vortices? They're spinning things. What happens when air spins? Centrifugal force flings it out. What happens when centrifugal force flings it out? It goes to low pressure in the center. What happens when it goes to low pressure in the center? You lift the damn airplane. The low pressure from the vortex is what lifts the damn plane. The airplane is lifted by the low pressure in the vortex. And here you can see it. Some guy put like little ink blob thingies on the bottom of his delta wing as the fluid was flowing this way. And you can see that air comes up around the leading edge, spins around, forms this vortex. The vortex has a low pressure in the center, and the low pressure is what lifts the plane. And as soon as I saw this, I was reminded of when I tuned the F-4 Phantom with an Israeli Air Force F-4 pilot, when we were getting all the performance of the Phantom absolutely perfect in X-Plane 12. Oh, and this is a new F-4 Phantom OBJ file that Rodrigo is doing. You haven't seen that yet, but you will. We'll come out with that in version maybe 12.1 or hopefully sooner. We'll see. But we're doing a whole new F-4 Phantom object to go with the new F-4 Phantom OBJ as well. But and this F-4 is incredible because I got the Israeli Air Force pilot dialing the aerodynamics with me. I got Rodrigo, who's the most amazing artist, doing all of the geometry. And then I'm going to see if I can get Daniela to find a way to do the sounds for the F-4. And when you get those, it's going to be like you are in a real F-4 when you fly that in X-Plane. So this will be X-Plane, maybe 12, 12.1. But I tuned the aircraft to fly perfectly with this Israeli Air Force pilot, Huss, I think is how he goes online. And that is an airplane that is lifted by vortex lift. The air forms these spiraling vortices that create a suction that lift the airplane. You see it here, you see it here. And that's also suddenly, clearly, how the horizontal stabilizer of an F-14 operates. Well, let me ask you this. Does the vortex-generated delta wing, or the vortex-lifted delta wing, does that work based on the component of air from the leading edge to the trailing edge? Or does it work on the longitudinal flow along the leading edge as well? The answer is the delta wing clearly wants the three-dimensional airflow. The traditional wing is only interested in the component of airflow that is going from the leading edge to the trailing edge. The delta wing is interested in the whole three-dimensional picture, including the airflow flowing along the wing. See, the component of airflow that's flowing along this wing is completely useless. The citation doesn't care about it at all. It accomplishes nothing. It's just running along the wing from the root to the tip. That doesn't generate lift. The citation only cares about the air going from the leading edge to the trailing edge. But the delta wing is a much more three-dimensional entity. He cares about the air going this way and this way, from the leading edge to the, well, where the trailing edge would be. But the longitudinal flow of air is what brings that air up and around and keeps it energized. So the delta wing wants the complete three-dimensional airspeed, not just a component of the airspeed. And as soon as I realized that, and applied the full speed of the airplane to the delta wings, including the stabilizer of the F-14, all of a sudden, the F-14 flew perfectly. And so just the most incredible thing about the F-14 is the main wings are acting like the wing of a Cessna when they're all the way forwards. It's just whatever the airspeed is, leading edge to trailing edge. They act like the wings of a Citation 10 as they start to come aft. The main wings only care about the component of air between the leading edge and the trailing edge, which is not your total speed as the wings get swept. But the horizontal stabilizer, which is a delta, needs the full three-dimensional airflow to form those vortices, and that's what let the stabilizer be as effective as it is. And a final little bit of hilarity of an F-14 is it also induces the biplane code in X-plane. Did you know that an F-14 is a biplane? It is. Look. I guarantee you these vertical stabilizers, one impacts the flow of the other. They're set up like this. This, it's all the same thing to an airplane. Who cares which way they're pointed? And so an F-14 does have biplane effect on the vertical stabilizers. Each one is a little bit less effective because it's in flow that's been slightly turned by the other. So the F-14, it's an unswept airplane. It's also a swept wing. The stabilizer is also a delta wing, and the vertical stabilizers are a biplane. So this aircraft is incredible, and we have all the physics for it in X-Plane 12. I highly recommend taking it for a spin. So that's the status of wing sweep, critical drag divergent Mach number, and delta wings in X-Plane 12. I'm pretty sure I finally got the code perfect, despite my little screw up between Beta 1 and RC2 that Mike pointed out for me. But I've tested this with a wide range of airplanes. I'm pretty happy with the code right now. So grab X-Plane 12 RC3 or later, which is out at the moment I'm recording this video, so you can't even get an earlier version. Get X-Plane 12 and give this stuff a try, either as somebody that just wants to fly airplanes or enter them into Plane Maker yourself.